This little test particle is a positive radius from a positive mass. Now it's a negative radius from a positive mass. Now it's a positive radius from a negative mass and a negative radius from a negative mass. That's done deal right there. That is a flawless mathematical description of everything I have just described. Now at this point, this is out of my hands. Now general relativity is predicting what I'm showing you. So at this point, I'd like to keep things a little fun. I'll place a bet available to anybody in the world, from Neil deGrasse Tyson all the way down. If you can prove me wrong on my interpretation of general relativity, I will give you my motorcycle. A 2000 Suzuki Intruder 800. Now in all seriousness, if you do prove me wrong and you say, hey, cough up that bike, it's yours. But if you're not worried about a motorcycle and you just disagree with my interpretation and you would like to somehow prove me wrong, and I'll do this whether you take the bike or not, I will change the title of this video from Black Holes Solved to Black Holes Still Not Solved. And first thing in the description, I'll say, although this might seem interesting, this has been proven false, and I'll give you credit if you'd like it. Okay, so while the physicists try to look at that and figure out why that's purely coincidental to everything I've shown, which they should, let's take the time to describe what these two lines mean to the average person with an interest in cosmology. All right, let's do this. So this is the equation for gravitational time dilation. Those lines that we saw before were a mathematical visualization of everything this has to say. Now this equation is derived from the Schwarzschild metric. And if you would like to see how this equation is derived from the Schwarzschild metric, I highly recommend taking a look at Eigenkris's video titled Relativity 108b, Schwarzschild metric interpretation, gravitational time dilation, event horizon. There will definitely be a link in the description to that video. All right, so moving on. The equation for gravitational time dilation tells us, in the vicinity of some massive object, how long would it take for a clock infinitely far away, unaffected by the gravitational effects of this massive object? Sometimes I like to refer to that as God's time. Usually it's referred to as coordinate time. How many seconds would it take for this clock to read a certain amount of seconds go by on this clock that is affected by the gravitational field of this massive object, depending on the radial distance of this clock from the center of mass of this object? Once again, this time, this mass, this distance from the mass. C, G, 2, 1 are all constants. G is the gravitational constant, C is the speed of light. And this equation is applicable to any type of mass, whether it be the Earth, the sun, a guinea pig, and especially a black hole. All right, so let's give a little example so we can help visualize this better. Let's say this person, infinitely far away from this massive object, wants to know how many seconds would it take to see 3 seconds go by on this clock. Now the person could either look through their telescope or just use the gravitational time dilation equation to calculate that. Given that this object is some mass, we haven't put in that number, we're just going to leave that. If the person is 10 meters away from that massive object. So we calculate it out, and let's say, for instance, we got that it was 7 seconds. It took this person 7 seconds to see 3 seconds go by on this person's clock when they are 10 meters away from this massive object. So what does this mean now? Say this is you and this is me, and you're seeing how long it takes for 3 seconds to go by on my clock. And you're looking at your clock and you see it takes 7 seconds. That means time is running slower for me in the vicinity of this massive object. You're saying to yourself, wow, I already had to wait 7 seconds to see even 3 seconds go by for Tom as he's near the black hole. You're saying, hurry up. Will you hurry up with your 3 seconds? Why? Because I'm going slow, and you don't like when I go slow. So stupid. If you're looking at your watch and you're saying, wow, it just took me 7 seconds to see 3 seconds go by on Tom's clock as he's close to this black hole, that means I'm aging slower. That means everything in the vicinity of this object is aging slower. And of course, the farther away we get, the less the effects of gravitational time dilation. The closer we get, the more the effects of gravitational time dilation. And that is what that is mathematically showing, those 2 lines. It is a plot of every single radius, given a certain mass and a certain time. How long would it take depending on how far away I am from it? So what is the equation for gravitational time dilation telling us? Where we have 0, negative radiuses, and positive radiuses. Where this right here is the event horizon of the black hole. I'll mark that. And this line will represent the asymptotical region of coordinate time. And so let's look at that. And also here is the singularity, a big bad singularity that I'm about to take care of here in a little bit. So what do we notice about this equation? This is telling us what we are on this side, what we already know. As we get closer and closer and closer, it takes more time to view a certain amount of time go by on a clock. That's in the vicinity of the gravitational well. And also we notice as time gets slower and slower and slower, notice at the event horizon that it goes to infinity. This is why it's said that if you view an object falling into a black hole, it will eventually freeze in time. Why? If it takes you very far away from a black hole, watching a clock fall in, if it takes you infinity amount of seconds to see any amount of time go by on that clock, then time has stopped for that clock. Infinity amount of seconds to see any amount of time go by on a clock means that clock falling in has frozen in time. And now what do we notice on the other side, the region of negative radius that was previously uninterpretable? Before I go on, I just want to say that as we get far away from the massive object on either side, it asymptotically goes to the coordinate time. Time goes 1 to 1. So what do we see on the opposite side? We see time getting faster and faster and faster as one approaches an object while on opposite sides. Remember how I showed in the 2.5 dimensional visualization? From a negative radius from a positive mass is on the opposite side. So that's it. I mean, when the equation for gravitational time dilation is predicting what you said flawlessly, and at the same time that description resolves the black hole information loss paradox, and explains pretty much every phenomena in the universe, you've probably figured it out. And I'm pretty sure I'm the first person to figure this out. If not, then I will gladly concede to whoever was the first person to figure it out. I would be stoked if I popularized this idea. I did totally figure this out on my own though. But who cares about all that? I'm just happy to explain it to you. Okay, so next thing. Here's the event horizon, here's the singularity. Now I want us to notice something else about this graph. This spot right here and this spot right here are both 1 unit of measurement away from the singularity and from the event horizon. These two are 2 units away from the singularity and from the event horizon. I want us to notice something about these numbers, and this is the case for all these numbers across the board. They are inversely proportional to each other. That means this number is this number divided by 1. And that also means that this number is this number divided by 1, this number, what, you get the idea. And that's for all numbers that are equidistant from the singularity on the negative side and the event horizon on the positive side. So what does that mean? I don't know, you tell me. I'm tired of figuring out everything. I'm kidding, I got this. All right, so why is that happening for spots that are equidistant on both sides? Can you figure that out? Why that's happening is because those two spots are at the same point of the fabric of space-time, but just on opposite sides. Think about it like this. If I have a massive object right here, and I'm this far away from it, let's say I would experience gravitational time dilation by 3. Now, if I'm on the opposite side in that same spot, now I experience it time by 1/3. This is due to the equivalence principle. At the same spot, the effects of gravitation must affect me the same. That's the equivalence principle. But since I'm on opposite sides, I experience the metric, the manifold of space-time, differently. So that's why both sides are inversely proportional to each other. If gravitational time dilation increases time by 10 for me on one side, then on the other side, it must be 1/10. And now, what do we notice about that singularity right there? Can you figure it out? You can figure out what the singularity is just from everything I've said. Part whatever, singularity. Alright. At the event horizon, it's infinity. What is the inverse of infinity? I'll give you a hint. The opposite of love is not hate, it is indifference. Make sense? 0. The inverse of infinity, 1 divided by infinity, is 0. 1 divided by 0 is infinity. That means the event horizon and the singularity are at the same points of the fabric of space-time, but on opposite sides. So what does that mean? That means that the singularity, incorrectly deduced to be the point of infinite density, and I'll explain why that happened later. So what is the singularity? The singularity is the same point as the event horizon of the black hole on the other side. So what does that make it? That makes it the opening to the scarlet hole. I figured it out, I'm naming it. It's called the scarlet hole now. Deal with it. Also, I'm saving the term white hole for the origins of the Big Bang. It's called the scarlet hole. I figured it out, I'm naming it. Deal with it. Okay. But it is the opposite of a black hole. A black hole, everything goes in. A scarlet hole, or a white hole as some of you know it, but you're not allowed to call it that anymore, because it's a scarlet hole, because I figured it out and I'm naming it. I really just want to drive that point home. Everything comes out of a scarlet hole. So this is the current Wikipedia page on white holes. And we can see how absurd things really get. Like black holes, white holes have properties like blah blah blah. They attract matter like any other mass. They don't. But if we assume they do, well, the next thing written is, but objects falling towards a white hole would never actually reach the white hole's event horizon. Now how the hell can matter be attracted to it but never reach it? That makes absolutely no sense. Anyway, moving on. Though in the case of the maximally extended Schwarzschild solution, the white hole's event horizon in the past becomes a black hole's event horizon in the future. So any object falling towards it will eventually reach the black hole horizon. This is a statement dreamt up by the utterly deranged. Every concept about white holes so far is completely flawed. And that is why I'm renaming it. It's now a scarlet hole. Remember when I resolved the black hole information loss paradox and I said how it seems like a black hole is just seemingly deleting matter? Well, it's the opposite for a scarlet hole. It would appear to be seemingly creating matter out of nothing. So any sort of civilization that lives near a scarlet hole, and that wouldn't be possible because it would be gravitationally repelled, would be as confused as we are about black holes. Why is it creating matter? Well, we say, why is a black hole deleting matter? Well, you could send them this YouTube video. So if both the opening of the scarlet hole and the opening of the black hole are equidistant from each other, then that means we would want to see some sort of interesting behavior going on halfway between the two, right there. But since those numbers are imaginary, the only way to see that is to plot the imaginary numbers. Now, these numbers are purely imaginary. They're not, they have no real component to them, so we are able to plot them on this, but just keep in mind that they are purely imaginary, meaning that they involve the square root of -1. Believe it or not, that's actually how I came across this. I was trying to mess with that and then figured out black holes from that. I never figured out the imaginary number part, but then I figured out black holes. Seriously. So, okay. So let's plot those imaginary numbers. All we can hope for is that we see some interesting behavior going on right there. Because imaginary time is, at the moment, uninterpretable. I don't know what it means. Stephen Hawking didn't even know what imaginary time was. All I know is I like it. I like it a lot. I have an idea of what it is, but I'm not going to talk about it because I'm not that comfortable with it. And we notice from this side, the graph is well behaved. Then you say, oh, there's a little break in the graph. A mathematician would say that's not well behaved. And I say, it's not well behaved. But don't forget, every imaginary number has a complex conjugate. Boom. Well behaved. I kind of have an idea of what's going on. I kind of want to talk about it, but I'm not going to. So, now, there is one really interesting thing that you can figure out about black holes from here. And I'm not putting it in this video. Why? Because anybody can just take this and run with it. I need to maintain some sort of leverage. If you want to steal this, then you're going to have to figure it out for your damn self. And maybe someone really smart could figure it out. I'm not saying I'm really smart, but yeah, yeah, I am. You fucking figured out black holes, are you kidding me? But, sorry, I'm being stupid. But there's a lot of things I'm leaving out of this video, just for the sake of, hey, if you want to steal this, you're gonna get stuck and you're gonna need to come back to me. Let's say I'm talking to you, the person that's saying, you know what? I don't care about your motorcycle. I'm totally taking this from you and running with it. Let's say you do that. And maybe you could figure out some of these things that I haven't put in this video. And there's a lot. There is one humongous thing that I know you will not figure out. Just like the black hole thing. If it hasn't been figured out in 107 years, then I doubt anyone's going to figure it out. Me telling you about this interpretation of the region of negative radius, there being two sides, you might be able to figure that out on your own. A lot of the stuff that I've left out probably be pretty hard. But there is one part that you will not figure out on your own. It's very mathematical. It took me a long time to come up with, but it's so beautiful. I wish I could put it in this video. But no one knows who I am, and someone could just steal it. So, yeah. It's something that if you want a fully quantized theory of gravity, you're mathematically going to need. And that is why I'm not putting that in this video. But if you ask me nicely, maybe I'll tell you. But yeah. I really wish I could, I really would love to just have it right there, right now, but yeah. So if you want to steal this from me, just know that you're probably never going to figure that part out. You will get stuck at the point where you need to quantize gravity, and you will have to come back to me and ask nicely. And at that point, it's going to cost you if you want me to tell you. And besides all that, I will turn your life into a fucking nightmare if you steal this from me. Alright, so what's going on with all this? We got the event horizon of the black hole coinciding with the event horizon in the math, right? Now we got the imaginary numbers halfway through, right there, halfway through. And now we can plot the event horizon of the scarlet hole. Let's see. So that would give us something like this. You enter the black hole, go through, and what is this right there? What is this? That's where it's going to the other side. That's the point at which regular matter becomes antimatter / dark matter and gains its anti-gravitational properties. And then it goes out and then exits out the scarlet hole. That point halfway between is where the edge of the fabric of space-time is happening. So at this point you might be like, wait a sec. I thought the singularity was a point of infinite density where all the mass is located at an infinitesimally small point in the fabric of space-time. So, physicists, mathematicians, everybody, why is that happening? Now, at this point, if you're someone with a casual interest in cosmology, go grab yourself a cup of coffee because, yeah. All right. So why are we getting this point of infinite curvature? Once again, we got the event horizon / singularity of the scarlet hole. We got the singularity of the black hole / event horizon of the black hole. So now let's get away all that superfluous material. We get something like this. Halfway between is the edge of the paper, if you will. Right there, boom, see that? That's where it goes over to the other side. So why is this right here appearing as a point of infinite density? Infinitesimally small point where all the mass is located. That is not real life. That is an error message. You're taking an error message. Physicists, you are taking an error message and relaying it as real life. That is absolutely not the case. In essence, what you're doing is trying to take one side of the fabric and drag it through a hole onto a side it's not causally connected to. That a light cone on one side cannot see. Because light does not reach the other side, no matter how fast it goes, and nothing goes faster than light, it cannot communicate with the other side, so it is not causally connected to the other side via light. Light is built into general relativity. And you're trying to take one side and bring it in. And right there, within the interior of the hole, the metric is forgiving. It still lets you try to continue downwards with positive gravity. But then right before you get to that opening, it closes off to a point of infinite curvature. I think it's so beautiful mathematically how general relativity gives its error messages. You're making gravity go inwards and inwards and inwards and inwards and inwards. Right there. And since we're only used to gravity working in one direction, you keep trying to make gravity fall inwards and inwards and inwards. At this point, the object is becoming antimatter and gaining anti-gravitational properties. That means what you need to be doing is taking the metric right there and going back out. See that? Going in, anti-gravitational effects acquired, back out. Not always positive, 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 because then you get that point of infinite curvature. The metric won't let you take it any further to the other side. Now at this point I just want to say, if a black hole is eventually evaporating over time, then that means the stuff that fell inside of it is eventually escaping out into our universe somehow. Unless you want to invoke the concept of a parallel universe or something equally absurd, you have to accept the fact that matter escapes into our universe. But no information can be acquired from it. That's why it's dark matter. And it has to gain anti-gravitational properties to escape. Antimatter. So That is the only way something can escape a black hole, is if it simultaneously becomes dark matter, which you can't get information from, and gains anti-gravitational properties. If anybody can explain that in any other way, how a black hole eventually evaporates over time, without giving me multiverse shit, go ahead, do it. There is absolutely no other way to explain it. There is only one way to resolve the black hole information loss paradox. It becomes dark matter. Dark matter has anti-gravitational properties. Due to a parity inversion, it must also be antimatter. Gravitational effects of antimatter are under question. I will address the CERN experiment during the questions part, because it only proves me right. But there's no other way. Parallel universes, say that for the movies. Wormholes to distant parts of the universe. I don't want to hear about them. So the last thing we'll deal with is space, and this part I'm going to go through pretty quickly. Alright, so let's do this mathematically now for space. And in order to bring that turnaround point to the origin, I'm just going to do a slight coordinate change in general relativity. The Schwarzschild metric. If you want to see the math for that, there it is. Look how beautiful that is. It's almost like it was supposed to be written that way. Gets that 2 out of there. So then we get that as the new metric. And in order to show this for space, now, since I've done this coordinate change, I have to take the integral of this beast right there. That might look simple, but that is an insane integral to take. Now, for the 1 minus 2 gm over c squared r, Eigenkris does a fantastic job taking the integral of that. So, congrats, you two. But for this, I would have to do a different integral. And I have a slightly different method of doing it than Eigenkris did. So we take the difference of 2 sections, and I must say that Eigenkris's video would complement this video extremely well if you would like a better description of this. At this point, I'm just trying to prove it. So at this point, we get that length is longer because space is being pulled in. Take a look at Flamm's paraboloid if you want to see how that works. Then on the other side, if you take the difference in the same spot, you would see that length is shorter. That's because gravity is pushing outwards. This proves that on the other side, shit is pushed away. On this side, stuff gets pulled in. And there's the interior region. If you take the difference between this, you actually get pi times the square root of -1, which is interesting. If we plot the imaginary numbers, once again, we get interesting behavior at the center, like this. I don't know how to interpret that. Yeah, that proves it for space, really. That's it. One other cool thing I wanted to show you, if we do that coordinate change and apply it to time dilation, we get a graph that looks something like this. That's the orange. And if we allow values of mass to change and values of proper time to change, then we get this beautiful motion right here. That negative mass, positive mass, negative mass, positive mass, and that's for all different positive values of proper time. Pretty cool. I know. All right. Oh my god, I'm finally done with this part. Holy shit.